Hi everyone, a pleasure to meet you here once again. The plan for today is continuing our focus on MR optimization, and this will be done by illustrating the features of a parameter that plays a key role in the routine MRI workflow. And I'm talking about the turbo factor. And I'm pretty sure many of you try at least once to speed up the scan by manipulating this parameter. So, what are the advantages and the drawbacks of doing that? Let's find it out immediately, but first, what do we mean with the term turbo factor? So, in turbo spin echo sequences, the turbo factor, or sometimes called echo train length according to the manufacturer we rely on, it defines the number of 180-degree refocusing pulses that are performed in every single repetition time. This parameter has a key importance since it basically determines how much we can speed up a TSC sequence compared to a conventional spin echo. Now, combining the recommendations provided in books and manufacturer material MR related, along also with a little bit of personal experience, I have developed this table which shows what could be an optimal range of values for the turbo factor or echo train length according to the type of sequence weighting we want to achieve. So the reason why we do not perform a T1 or PD weighted sequence with a turbo factor of 24, for instance, is that the higher the turbo factor, the more the resulting image will display a mixture of weighting, since basically more data will be collected at the wrong TE. And this might end up in a more significant enhancement of the T2 contrast on our image. As a result, to be on the safe side, I would say better to stick with a turbo factor of 2 or probably 3 for a T1 sequence, and I would say probably 6 or 7 for a PD sequence. Now, the question is, why then sometimes we tend to extend these values over these recommended ranges? The explanation of this could be this formula. As we can see, technically speaking, increasing the turbo factor can bring to a reduction of the scan time. And this is because there are more phase encoding steps that are performed per each repetition time. However, this does not come completely for free, and such change might have some disadvantages. Firstly, extending the values for the turbo factor can make image blurring much more pronounced, and we'll explain why shortly. Secondly, this can also lead to an increase of the minimum TR. The reason for that is that longer echo trains could require a significant increment in the interval of time needed to acquire the necessary data, resulting sometimes in longer overall scan times, which is, if you think about it, completely the opposite outcome compared to what we usually try to achieve by boosting the turbo factor. But let's go through some specific examples on our MR scanner to better understand how this parameter works. So first and foremost, to find it, we need to navigate through the sequence tab, then part 1 submenu, and go on the bottom right of the tab. Now that we have located the parameter, let's think about the sequence that we want to alter. So we have here a TSC-T1 sequence with a turbo factor of 3 and an initial scan time which is just over 2 minutes. Let's see what happens if we gradually increase the turbo factor. So even a minor change from 3 to 4 will require an adjustment of the minimum TR, which as we said is going to increase. Despite this increase, the scan time is reduced as more phase encoding steps are performed in a single TR. Let's try to increase it even further. Again, as you can see, the TR increased, but the scan time is marginally reduced a few seconds. Now, let's exaggerate. Let's bring it to 9, which is 3 times higher of our initial value. As we can see, the TR has basically more than double compared to the one we had at the very beginning, which was around 700 milliseconds. And therefore, now we are definitely moving away from a value which could be defined as appropriate for a T1 sequence. What we can consider doing perhaps is increasing the number of concatenations to go back to a more suitable TR value for this T1 sequence. However, better bear in mind that this strategy that we are performing at the moment can also increase the number of motion artifacts on our image, so probably not exactly the best idea from a workflow perspective. Image quality wise, what are the main differences? So we have here on the left side of the screen a coronal T1 of the knee acquired with a turbo factor of 3, while on the right we have the same sequence but acquired with a turbo factor of 9, so 3 times higher. Some of you might have already spotted some blurring in the images with a higher turbo factor, and this is mainly due to the low signal present in the last additional echoes obtained. This can also boost things like motion and signal decay. If we zoom a little bit closer, in fact, it can give us a little bit the perception that some details are less clear maybe in the image on the right, and this is particular because blurring start to be pretty pronounced here. Now let's try to repeat the same process with a proton density sequence instead. We got here specifically a turbo spin echo Dixon with an initial turbo factor of 7, which we are going to double and bring it to 14. The initial scan time was 4 minutes and 33 seconds. Now we have cut the time to just over 4 minutes, but the machine is asking us to bring the TR up of a value which is almost twice as high as the initial one. Does a TR of 6000 work for a proton density sequence? I would say probably, but it also depends on the strength of the magnetic field that we are using. We might spot some changes on the image contrast though. Let's see. So, water-only Dixon image on the left was acquired with a turbo factor of 7, in contrast to the one on the right, which was obtained with a turbo factor of 14. Image blurring here seems overall less of a problem compared to the example displayed before. This is probably due to the type of sequence used. Dixon, we know, is pretty robust, less sensitive to magnetic field inhomogeneity, and probably in this sense less affected by potential blurring artifacts. However, some signal change starts to be pretty visible, I would say. You can see how the fluid became suddenly more bright as a result of the boost in the TR value. It might not be a major problem from a diagnosis point of view, but again, we need to be careful when altering TR and TE, as we might gradually change the weighting of the sequence. Last but not least, let's apply some changes on our T2 TSC sequence. We got here a turbo factor of 15 and an initial scan time of 4 minutes and 21 seconds. As we can see, we have brought the turbo factor from 15 to 20, and what happened? The minimum TR has increased, but also the scan time has grown a few seconds. It was 4 minutes and 21 seconds before, right? And this is exactly for the reason we mentioned at the beginning of the video, meaning that the interval of time to get the data is now as such that even if the ATL has increased, the result obtained will be a longer scan time. Bear in mind that this process is not linear, so if we keep incrementing the turbo factor as we are doing at the moment, we might still get the benefit in terms of scan time reduction at some point, like now, where we went down to a scan time of 4 minutes and 15 seconds with a turbo factor of 26. But again, is it really worth it? What's the impact of this on our image quality? So the next comparison will hopefully help us to clarify a little bit more our ideas regarding this. On the left of the screen we have our XLT2 TSC acquired with a turbo factor of 15, whereas on the right, for comparison, we have performed the same sequence but with a turbo factor of 30. From this evaluation, I think we can all agree that there are no major benefits on the resulting image quality after increasing the turbo factor. Actually, I would say that, as happened for the TSCT1, the component of image blurring has slightly grown where a higher turbo factor was used. Furthermore, one thing that we have not mentioned so far is the fact that doubling the turbo factor could also increase significantly the energy deposited in patients' body tissues, as there are more 180-degree refocusing pulses applied over a short period of time, with potential negative consequences on the SAR. As a result, for a number of reasons, we can easily say that such alteration under these circumstances has been pretty pointless. So guys, I hope this has helped a little bit to understand what are the main considerations to make before applying changes on the turbo factor for the aim of reducing the scan time. My advice is stick with the recommendations given with the weighting table that we explored before. There are definitely some other parameters that it might work to try to manipulate it before thinking about bringing up the value for the turbo factor. Having said that, guys, as usual, I will see you around.